Hello everyone, so today we're going to continue with subtopic 2.3, which is Hesss Law. So for Hesss Law, our learning objectives will be to state what Hesss Law is, and then we're going to apply Hesss Law to calculate our delta H, which is enthalpy changes, using Algebraic Method, method 1, and energy cycle method 2. And then we're going to illustrate the dissolution process of ionic solids. So how does your ionic solids dissolve in water? So Hesss Law. What is Hesss Law? It states that when reactants are converted to products, so we have our reactant X and product Y, the change in enthalpy is the same, delta H is the same, whether the reaction takes place in one step, one step meaning in this diagram here is delta H1, just one step process, or in the series of steps. So series of steps means there's more than one steps. So whether it is delta H2 plus delta H3, it will equal to delta H1, we go through this route, or we can have 3 steps, 1, 2, 3, delta H4, 5, and 6, we go through these steps to produce our product Y. So from there, when we write it in terms of equation, we know that delta H1, the one-step process here, from our reactant X to product Y, is equal to delta H2 plus delta H3, or is also equal to delta H4 plus delta H5 plus delta H6. So let's say if we want to find delta H1 and we have delta H2 and delta H3, we can find delta H1 by just adding them up. So if we have delta H1 and delta H2 and we want to find delta H3, so we'll just have to rearrange our whole equation to get the enthalpy change that we want. How do we use Hesss Law? So as we know that it is not possible to define the absolute measure of enthalpy, maksudnya we cannot measure enthalpy directly, but you can measure enthalpy changes. So Hesss Law will help us to calculate our enthalpy of reaction using the delta H that we have, K1, delta H2, delta H, so on. Another application of Hesss Law is to construct Born-Haber cycle, so we will look at that later. So there are 2 methods to calculate our enthalpy change, delta H. It will be algebraic method and energy cycle method. So we're going to look at algebraic method first. Alright, so our first example is using algebraic method. So given these thermochemical equations where we have our reactants and products, right? Reactants and products and the enthalpy changes, you are going to use that to calculate the delta H for the decomposition of hydrogen peroxide. So hydrogen peroxide, H2O2, decomposed into 2 moles of water and 1 mole of oxygen gas. So what is the enthalpy change for this reaction? This is what we want to find. So step 1, we want to identify the target equation. So this is our target equation, the one it's delta H that we want to find. And then we are going to look at the target equation left hand side and right hand side. So left hand side you have 2 moles of H2O2 hydrogen peroxide for our reactants and 2 moles of water and 1 mole of oxygen gas on the right hand side. So we want 2 moles of H2O2 on our left, so we are going to look at the thermochemical equation given. So find H2O2. So we have H2O2 here on the right hand side of this equation. So what you're going to do is you need to put this one on the left hand side. So what you have to do is you will be reversing this whole equation, because we want it on our left, following the target equation. So I've already reversed my equation, alright? So that means my sign has changed, alright? And then next we're going to look at the stoichiometry coefficient. So you have 2 moles of H2O2 on in your target equation. That means you have to times the whole equation with 2, alright? So what will we get? So this will be 2, 2, 2, and then times 2 for this value, delta H, you will get plus 375.8 kilojoule. So that means we already have our 2H2O2 on the left, right? And then we have 2 moles of hydrogen gas and 2 moles of oxygen gas on our right hand side. But here we have 2 moles of water and 1 mole of oxygen gas. So that means that we need to have water. So next we're going to look at your second equation. Okay, so here we have water on our right hand side already, but the stoichiometric coefficient is just 1 mole of water. Here we have 2 moles of water. So that means you want to times 2 this whole equation to get 2 moles of water. So that's what I'm gonna do. You don't need to reverse this equation because our water is already on the right hand side. So this will be 2. This will be cancelled out because it's times 2, and this will be 2. Okay, so that means you're going to times 2 here, and you should get minus 571.6 kilojoule. Okay, so right, so now that we already reverse and multiply the equation that we were given, okay, so now we're going to add up the equations and the delta H together to produce our target equation. Okay, so you need to be good at manipulating these chemical equations to finally get your target equation. So you're just gonna add up. Okay, so here we have 2H2O2, and right here in the bottom equation you don't have any H2O2, so this will be just brought down. Okay, you're just going to bring down that one, 2H2O2, and then you have 2H2 gas here, and here we have 2H2 gas. So what you're going to do is you're going to cancel out these two. Okay, so I'm going to use this color. This one and this one is the same, okay, but they are on opposite sides. So this is on right hand side, this one is on left hand side. Okay, we see this arrow, right? So they're going to cancel out each other. Okay, so to cancel out, that means you don't have any more H2 gas in your target equation. Okay, next you're going to look at your oxygen gas. So here you have 2 moles and here you have 1 mole. So this one is on the right hand side, this one is on the left hand side. So what is going to happen is that you will 2 minus 1, that means you will get 1 oxygen gas left, but it will be on your right hand side because kat sini yang lebih. Okay, so that means you will get 2 minus 1 oxygen gas on your right. Okay, next on the second equation, what is left? Since this one and this one has already cancel out each other, yang ni tinggal 1. Okay, let me just show you this one and this one. Ini tinggal, ni kosong, ni tinggal 1. Right, so this one is left, so you're just going to bring this down. Okay, so it's on your right hand side. So that is your chemical equation. So what will happen to your delta H? You're going to use this and this. You're going to add these two up together. Okay, so how much will you get? Minus 195.8 kilojoule. Okay, for the decomposition of H2O2 hydrogen peroxide. Okay, so that is your answer. Okay, now you have your delta H naught for the decomposition of hydrogen peroxide. So you have to make sure that your target equation is correct lah. Okay, kalau tak, that means that you might have gone wrong somewhere at these two steps. Okay, alright, so our second method is energy cycle method. Calculate the standard enthalpy. Okay, standard maksudnya delta H, standard not of formation of ethane C2H6 gas. So given the following data, we have the standard enthalpy of combustion for carbon graphite. Okay, this is the value. Combustion of hydrogen gas, combustion of C2H6 gas, okay, your ethane. So sometimes they will give you the chemical equations, but in this case they did not give you, so it is very important for you to be able to write thermochemical equations, right? So let's start with writing the thermochemical equation of combustion for carbon. So as we know, the definition for combustion, okay, delta HC, is when 1 mole of substance is being burned in excess oxygen, right? So that means we need to know that carbon graphite will be burned in oxygen gas, okay, to produce carbon dioxide gas, alright? So you have to make sure that your chemical equation is balanced. So we have one carbon, two oxygen atoms, okay? So the delta H will be this, alright? So we have to follow. Next, we're going to write down the thermochemical equation for hydrogen gas, okay, the combustion. So we have hydrogen gas molecule plus oxygen gas. You will get, okay, you have hydrogen and oxygen. Hydrogen being burned, you will get water, okay, water vapor. So the delta H will be minus 286 kilojoule per mole. Okay, so the thing is your chemical equation balanced already? So obviously it is not balanced, right? So because we have two hydrogens, two oxygens, and here we have one, so we need to make this 2, okay? Or if you do that, what will happen? You will have to put 2 here. Is that correct? Well, actually, this is not what we should do because we want to maintain 1 mole of substance that is being burned. Okay, because our definition of combustion is 1 mole of substance that is being burned in excess oxygen. That means that we have to make sure that hydrogen gas stays as 1 mole. So take that back. You're not going to put 2 here. So instead of putting 2 here and here, you are going to change this one to 1 over 2, okay? So once you do that, it means that you have 1 oxygen here and 1 oxygen here as well, and this is 2 hydrogens, okay? So with that, you will maintain, okay, the 1 mole of substance being burned, tally to the definition of combustion. Next, you're going to write down thermochemical equation for combustion of C2H6, your ethane gas. So let's write C2H6. Okay, when you have hydrocarbon being burned in oxygen, you will get carbon dioxide and water because you have carbon and hydrogen. So carbon dioxide and water. Okay, your delta H will be minus 1560 kilojoule per mole. Okay, so now we're going to make sure that this stays as 1 mole, the substance being burned, and then we're going to balance the whole equation. You're going to balance hydrogen. You have 2 hydrogens here, you have 6 hydrogens here. That means you're going to times 3 there. So now you're going to balance your oxygen gas. Here you have 2, here we have 4 plus 3, so that's 7. That means you're gonna have to put here 7 over 2 so that you have 7 oxygen gas here. Okay, so now that you have maintained 1 mole here being burned in oxygen gas, okay, and your chemical equation is already balanced. Next, we will be doing the energy cycle method. So you're going to start with your target equation, okay? So we want enthalpy formation of ethane C2H6 gas. That means you have to know how to write the thermochemical equation for your target equation, which is delta H formation of ethane C2H6 gas. Okay, so this is combustion of C2H6, not formation. So formation, if you recall the definition, it is formation of 1 mole of substance from its elements in the most stable state. So delta H formation of C2H6 gas will be, okay, from carbon, okay, carbon graphite, the most stable form of the element, and hydrogen. Kalau hydrogen gas molecule. Okay. And then you will get C2H6 gas. And you have to make sure that this stays as 1 mole. Okay. So delta H not formation of C2H6 will be so we want to find that. Okay. So now we need to balance our chemical equation. Here we have 2, here we have 6. So here we have 2 hydrogens, here we have 1 carbon. So first you're going to balance your carbon lah dulu. So we have 2 carbons, okay, and then we need 3 moles here to have 6 hydrogens, okay. So that will be your target equation, okay. So maksudnya we will have this one up here, and then we will be using these thermochemical equations that we already have the values of its enthalpy changes to incorporate in the energy cycle to form our target equation. So we want this delta H, okay. So now we are going to look at the equations that we have, okay, and how do we incorporate it into our energy cycle. So what I like to do is I look at what I want to form. It is C2H6. So I'm gonna look here. Okay, what do I have? I have C2H6 here. That means that somehow I will need to have something to form C2H6, which is this. So this will be here, and then it will be formed from what? We need carbon dioxide and water. So that means this plus this will form this and this, right? So that means I need to have carbon dioxide and water, okay. And then it will, okay, kalau ikut our chemical equation, you will get 7/2 oxygen gas, gitu, okay. So how do we get this? This is actually from our 2 other chemical equations. We have here carbon dioxide and water. So now we just use what we have here to form our carbon dioxide and water, and then from here carbon dioxide and water, okay, we can somehow get our C2H6 in this energy cycle method. But you have to follow the arrows that you already have, okay. But if you, let's say, change the direction of the arrow, reverse the equation, that means you have to also reverse the sign, alright, in our energy cycle. Okay, so what I'm going to do first is I'm going to take this one, okay, from carbon graphite. So we have 2 carbon graphite here. So plus oxygen gas, I will get carbon dioxide. So just draw an arrow, plus oxygen gas, okay, you will get carbon dioxide gas. Okay, so the delta H will be minus 393 kilojoule. Okay, and then but here we have 2 moles of carbon graphite in our target equation, right? So that means we have to times the whole equation with 2. So that means this one here, this equation kena multiply by 2, okay, ikut the target equation. So that means I'm going to put 2 in front, 2, and then this will be times 2, okay. So I will get the value lah, okay. So here you will get carbon dioxide gas 2 moles, okay. Alright, next you're going to form water, okay. So here we have hydrogen gas. So here we have hydrogen gas. It means you're going to react it with half of oxygen gas molecule to get 1 mole of water. So let's draw that. the arrow plus half oxygen gas. Delta H will be minus 286 kilojoule. 1 mole of vapor, water vapor. Okay, again, you have 3 here. Okay, that means you are going to times the whole equation with 3. Okay, so maksudnya kita times 3 lah. So this will be 3 over 2. Okay, this will be 3. And this will be times 3. So now that we have 2 moles of carbon dioxide and 3 moles of water, okay, if you realize, you actually have them here in this thermochemical equation, right? So actually, the reverse equation of this, okay, of this, will get you C2H6. So what I will do is I will just follow this equation, okay? So maksudnya C2H6 will react with 7 over 2 of oxygen gas to get this. So we just follow, react with 7 over 2 of oxygen gas, 3 moles of H2O and 2 moles of CO2, right? Okay, so this delta H will be, follow je because the arrow, I did not change the sign. I did not reverse the arrow, so I will not change the sign of my delta H. Okay, so this is my delta H, 1560. C2H6 react with oxygen gas, you will get this. Okay, okay, so how do we find this? The delta H formation of our ethane gas. Okay, now that we have done this energy cycle correctly, we have formed this energy cycle, I will tell you that clockwise equals to anti-clockwise. Okay, so that means this arrow clockwise will equal to anti-clockwise. So I'm going to put delta H 1, 2, and 3 so that it will be easier for us to refer. So this will be 1, 2, and 3. And this will be delta H formation. Okay. So since clockwise equals to anti-clockwise, so we have our clockwise being delta H formation and also delta H3. So that means I'm going to write delta H not formation plus delta H3 equals to anti-clockwise, which is this one. Okay, delta H1 plus delta H2. And then since we want to find delta H formation, we will have to move this one to the right. So you can do that, or you can just put in your values first. Delta H3 is minus 1560 kilojoule per mole. Okay, I'm just going to put kilojoule. Delta H1 is minus 393 times 2 kilojoule plus delta H2 is minus 286 times 3 kilojoule. To get delta H not formation, we just have to rearrange our equation. So your delta H formation will be minus 84 kilojoule per mole. Okay, that will be your answer for the enthalpy of formation of ethane C2H6 gas. Okay, so you have to make sure you know how to write thermochemical equations correctly. Remember the definitions. Per mole refer to who, and then you want to balance your equations here, okay, and times or reverse your delta H, okay, and then just incorporate the chemical equations into your energy cycle, and then follow this rule, clockwise equals to anti-clockwise, and rearrange to find what enthalpy change you want. Okay, right. Besides that, we can also find the enthalpy change of the reaction from enthalpy of formations. So let's say this is our chemical equation. We want to find the enthalpy change for the reaction, be it combustion, atomization, neutralization, whatever, okay? So we will need to use the enthalpy of formation of our C and D times with the stoichiometry, okay, that will be your product, okay, sum of delta H formation of all the products minus with sum of enthalpy of formation of all the reactants, so A and B. So here is how you will calculate it. You have to get the enthalpy of formation of A times with the stoichiometry A, okay, and B times with B, okay. So from there, your products minus reactants, you can get the enthalpy change of reaction.